everyone. So we're back here with some Sudoku and differential data flow. We did a few videos earlier about writing a Sudoku solver in differential data flow, and we're going to return to that now because the internet is excited about Sudoku in a sort of interesting way, and I wanted to check that out too because I'm also excited, to be totally honest. In particular, there's this puzzle which I'm going to flip over to now that you may or may not have seen floating around on the internet. Is a Sudoku puzzle. It's called the Miracle Sudoku, or that's a set of rules, at least, that make apparently under constrained Sudoku problems like this possible to be solved using a bunch of interesting bits of reasoning. And the place that I first saw this was on Cracking the Cryptic, which is among other things, a YouTube channel where these folks talk through generally interesting modifications to Sudoku problems is what I've been watching, at least. And it's quite stimulating, and I recommend everyone check it out who hasn't yet. But just to give you a sense for why these types of Sudoku problems might be easy. You can watch the video. Definitely recommend it. I'll try to link it below in the description. But let me talk you through the rules that they would talk you through in explaining these types of problems. So this particular one we're going to look at, this very simple puzzle with a 1 and a 2, has some additional constraints. So first of all, the normal Sudoku rules apply. That means that in every row, column, and 3x3 cell, each number 1 through 9 can appear only once, exactly once, in fact. But additionally, there's additional rules here that any two cells separated by either a knight's move or a king's move in chess can't contain the same digit. And right now we're seeing that this 1 in the center, for example, can't it prevents a 1 from appearing in either of these two highlighted squares, or indeed any of the 8 highlighted knight's move squares around it, or the sort of diagonal king's move squares. The immediately adjacent squares are going to be ruled out by this normal Sudoku row and column rules. So we'll draw a picture of that just to be super clear. There's one more additional rule too, but this would mean that for any square like a 2 here, we block out all of the rows and columns. We're also going to block out this cell, but we'll hold off just a moment to do that. No, we can do it anyhow, I guess. Blocks out the cell, but also blocks out a few more things. Knight's moves and king's moves are blocked out. So each number blocks out a fairly large region around it, right? This big diamond-shaped region around it. We get this additional little piece over here because it's in the same cell, but otherwise pretty big region around each of these numbers that just can't be the same number again. And so that's like a much stronger constraint imposed on all of the space here, which makes it starts to impose real constraints on where we might find other numbers like 1 and 2. And potentially then even larger numbers. All right. There's one additional rule here which is going to make this tractable, which is that any two orthogonally adjacent cells, meaning side to side or above below, cannot contain consecutive digits. So this 1, for example, prevents a 2 from being immediately to the left, right, up, or down. And more generally, you've got a larger number. There can be numbers both 1 larger or 1 smaller, neither of which can be immediately to the left, right, above, or below. So these are just some additional rules. So we have already a Sudoku solver written, not a great one, but we could try to run that and see where we get. We're not going to get very far, it turns out, but we can also go and add in these new rules. And I thought we'd do that and sort of see how much progress we make. I've actually, seen the puzzle be solved already. I didn't do it myself, but I do know that we get some way through the puzzle using these sorts of rules, but eventually we need to get to slightly smarter rules. And what I'm hoping to do is get at least that far. And I can explain what the slightly smarter rules are. They're not super complicated, and they're totally things that we could write down in differential data flow. But we'll see when we get there how much time we've taken and how painful everything is, and whether the right thing to do is to let it go for our next video or to try to barge ahead and see if we can't make some headway. So, let's go back to our Sudoku code in Differential Dataflow and get reminded about what's going on there. And then we'll key in this problem. We'll probably run it first and see that we make no progress whatsoever. And then try to start writing in some rules. So here we have our Sudoku solver thing, which we can make a little bigger. And we can get rid of the output for the moment. It's a program it's about, I guess, 200 lines long now. Some hunk of this is a little bit of a driver program. This part up here, so the first 100-ish lines, I suppose, start up a timely data flow computation, prepare some input, and load up the input essentially into the computation. So it wanders around, basically spitting in the initial values. This is a more well-specified Sudoku problem, but one that doesn't have any additional rules. And what we're going to do in this Sudoku problem is repeatedly iterate on the possible values found in any row column location. And we're going to start with some specific values in specific locations and some utterly unspecified, or 9 possible values in each other location. And then we're going to take that board state, which is initially just, well, it's going to be some processed version of this. Basically, each row and column is going to contribute a bunch of different things, and we'll then iterate on it. Or we'll see in just a moment, I suppose. But we will iteratively develop this board state, imposing or sort of using the fact that constraints are imposed on various locations to try to narrow down the candidates for particular locations, which will hopefully allow us to draw more and more conclusions. Eventually, ideally, we will reach some sort of fixed point, because we'll see that the way we define the rules only constrains the board more and more, and once we stop producing new constraints, we stop the iteration and we see what we get. And that may or may not be a unique board state. In fact, we're definitely going to see some non-unique board states, which is fine. It's just a natural consequence of not having implemented enough inference rules. Yeah, but we'll see how that goes. All right, so this is all just sort of loading stuff up and inserting initial locations, I suppose. No idea. Oh yeah, sorry. And then the experiment that we were doing when we run this thing, just sort of run it off to the side here, is a little interesting. No one gets to do that. We're running our little Sudoku solver, and it's reporting how many times do we see cells with this many distinct values in it. So at the very beginning, with all of this input loaded up here, this initial board state, we end up in a world where each of the 81 cells has exactly one representative there. Different numbers, 1 through 9, but only one, which means we found a unique solution. And then our experiment was to walk through just in order of those cells and replace specific values with unknowns, basically start erasing givens for the beginning of the problem and see what happens. And what we see, and this is meant to be sweet because things like differential data flow are relatively good at incrementally updating iterative computations, which this will be. We haven't seen that yet, but so we peel out each of the initial specified values, and it turns out that for a little while that's okay, 2 rounds, and eventually we start to get into a situation where instead of every location being uniquely determined, some locations have 2 possible values. And that's, again, this is a natural state for an underspecified Sudoku problem, or potentially, if we haven't put in enough clever inferencing rules, all that really means is that the set of rules that we've written down reach a fixed point, reach the limit of their reasoning abilities without narrowing down the solutions to exactly one board. And that could be because there are multiple solutions. It could be because there's some clever reasoning that we're not doing. For example, we're just applying these rules that I'm about to show you over and over again. We're not speculating on values in particular locations, or trying out all possible board states in an efficient way. So let me just walk you through the rules. They're not super complicated. In fact, they're like really simple. There's much more clever things that one could do, and hopefully actually we'll see that we have to do them. So so this method that we've written, Sudoku over here, takes us from a collection of triples, U8 triples, which are essentially going to be val, row, column triples, each of which means it's still possible that this value could appear at this row in this column. So this value could appear in this grid cell location. And we expect to have a lot of these to begin with. Some grid cells may only have one value if they're given. Others, at the very beginning at least, will have all 9 possible values. And this routine, the Sudoku thing, is going to produce as output some restricted version of this, a subset of these initial possible assignments, but restricted down based on constraints that we've applied. And if we're lucky, it'll be relatively compact. One thing to point out is, although there can be exponentially many Sudoku solutions in the size of the board, which whatever, this representation is still relatively compact. Like we can have at most 9 times 9 times 9 values here, just because that's all that there can possibly be. And so as we restrict these things down, they get smaller, but they're never exponential. We're leaving sort of unexpended a potentially large cross product. We're just keeping it in a more compact representation. Anyhow, which means, among other things, we're not speculating and doing things that might take exponential amounts of work. But let's talk through the rules, just to remind you all. If you remember, good for you. I certainly didn't, to be totally honest. But what we're going to do is we're going to start from this collection of candidate value row column triples, and we're going to call differential's iterate method, which starts from some state and then repeatedly applies rules, basically repeatedly applies a lambda that takes us from whatever the current state is. So we're essentially describing the update rule for the board state. So if we start from a board state here, and actually we could just call this board, couldn't we? No, not if I... Great. So we've got, hopefully that, we'll see if that correctly changed everything or not. We might have to undo it. But from some particular board state, what we're gonna do a few different things. In principle, these could all be done in parallel, but the rest of the code has to be written in sequence, so we're gonna write them in sequence. We are going to first say, are there any locations that are uniquely determined, in the sense that there's a row and a column with exactly one value. Right? Now, if so, that's really good to know, because that's a constrained location that imposes and restricts the possible values of the locations around it. And the way we do that, this little bit of logic here says, well, take any val, row, column, triple, just keep the row in the column, and then we're going to apply this threshold method in differential, which essentially lets you say, for some incoming data, look at their count, and based on their count, do something. In particular, produce a new count for the output. So look at these incoming row-column pairs, and what we're writing is, if the count for any row and column is exactly 1, that's really exciting. Let's keep it in the sense that, let's have the resulting count be exactly 1. And if the count is anything other than 1, if it's 0, which, to be honest, we shouldn't see because the data just won't be there, but if it were 0, if it's 2 or 3 or anything like that, produce a 0 as output. Basically, in that case, delete the record. The collection in the output, it will only contain those row-column pairs that occurred uniquely in the input. So we've got a collection now of that. We've called it determined. And what we need to do a little bit of a semi-join thing here to pull out the actual row call vals. So we just determined the locations row and call. we didn't figure out what the value was when we did this. But let's do that. Let's do that here. We're going to do a little semi-join to pick out the actual row column that were uniquely determined. And then we're going to apply a bunch of exclusion rules. And this is a place where we're going to add a few additional constraints corresponding to these knights moves and these orthogonally adjacent numbers that are within one of each other. What we've written instead here are the normal Sudoku rules, which are the any determined location excludes all of the other values that are in the row and column. Sorry, in the row for this one. This rule excludes all of the same column, all the values in that column. So we're building up rows and columns that and values that cannot be, and we're eventually going to delete them essentially from the set of candidates. And same thing with a cell. If there's a determined location, everything else in its cell needs to be absent. Basically, we can't have that value anywhere else in the cell. And this logic is a bit more gross because it was really easy to just delete a row or column and replace the field by 1 through 9. And walking through all the different rows and columns in the associated cell is just a bit more gross. And then we're going to take all of our exclusions, okay, put them all together, put them in the right shape, negate them so that they contribute negatively now. Throw them in the mix with our board, and then keep only those things that count up again to exactly 1. So if essentially, in our input board, all of the invariant is meant to be that all of the rows, columns, and volumes triples are present with multiplicity 1 or 0, meaning they're absent. And as soon as we get any negation in here, we are allowed to go and just delete the entry. Not allowed, sorry, but obliged, really. So this is all that we're doing again. We wander through our rows and columns, and if the count ends up being this is a bad name. It should have been row call val, basically, or val row call. It looks like I copied and pasted it from somewhere. Let's change that while we're here. So if that has not been negated for any reason, keep it around. Otherwise, set it to 0. If there's only one negation, it would go to 0, but there could be 2 negations or 3 negations, and the count could be -2 or -1 or 0 or anything like that. So we're just going to zero it out. And now what we have are the legit candidates, and we could stop here and cycle back around. And in fact, we did this in our very first video, this sort of simple set of inferencing things where we literally just look for determined things and delete possibilities based on those locations that are determined, hoping that causes some other location to now become determined. So this is a sensible breakpoint to sort of think about, well, we could stop here if we wanted. We didn't, though. We proceeded to write a bunch more. It's pretty verbose logic, but it's actually doing something relatively simple several times. So what it's doing is essentially this determined logic, actually, over and over again. But what it's doing is, instead of looking for rows and columns with just one value, it's looking for values in rows with just one column, meaning for a given row and a particular value, if there's only one column that exists in our candidates, that's pretty exciting, because that means that this value, which does have to occur in this row, can only occur at this column. So that locks in another val row column triple. So we're just writing that down again. We're putting the data into this val row format, and then we're asking if the count is exactly 1, make a note. And then we're doing a semi-join like we did before, announcing essentially these things need to be locked in. This is semantically different than up above, where this was going to be things that kind of needed to be, they were uniquely determined. This isn't a set of uniquely determined things, but it is a set of things that need to be true and potentially need to delete any potential peers. They can be used now to block out other folks in their row or column or cell. So we do that for rows. We do it also for columns. That's right. So if a value in a column thing occurs in only one row, great. Let's lock that in. And same things with a cell here. If a particular value occurs only once in a cell as a candidate, that's got to be the place. And with all of these things specified, we can essentially lock these values in. So we were just saying down here that if we have things that need to be locked in, basically we can delete anything at a location that should be locked. Right, so these locked things, which are the concatenation of all of them with a distinct. Any entries at their row and column, just delete them, and then we'll add in the locked things that we know to be true. So we saw last time that this gave us a little bit of lift in the sense that we could derive some more things than with just the rules up above. If we go and try to load this up now though with our new Sudoku problem, so lots of fun things happen over here on the right hand side, lots of updates were made. What we are going to do now though is to change the input problem. I'm going to try to change it to be this nice thing here, which is going to be a whole lot of periods, one bunch of periods, two, and then a whole bunch of periods. And we'll see if I can count the right number of times to put in the right number of periods. The structure is all of these folks, then these folks, and these folks in a 81 character long string. So let's copy this, paste it down. We'll comment this little fellow out for the moment. And we're going to want to put in here how many? 4 times 9, right, is 36, plus 2, 38 periods. So I suppose what we could actually do to make our lives easy. So let's just delete this whole thing. So this is 9 periods. And we're going to want to paste that down 1, 2, 3, 4 times, followed by 2 periods, and a 1. And a 1. We're going to want to follow that by 9 plus 3, 12 things, right? 6, 12 things before a 2. So let's paste down 9 and do 1, 2, 3, or 2. We're going to do 2 things, 2 periods, and then 1, 2, 3. And that should be, let's check, the same length. Oh, looks good. But we expect it to be much less productive in terms of running the problem. Now, if we were smart, we could have had this actually be a supplied input to the thing so that we wouldn't have to recompile each time. But that's why we're not going to recompile too many times. We're not going to be changing the input too many times, so that's not going to save us a lot. Hopefully we'll change the program a bunch because this isn't going to work out very well. Great. All right. So, well, what do we see here? We need to. Oh, right. Okay. Sorry. So, try to get my head around why these changes are happening. So this is the initial final counts. So in this particular problem, we started iterating, and not a lot of great success was had. 2 locations were determined. That's clearly the 1 and the 2 here. 6 locations had 7 candidates. 28 locations had 8 candidates, and 45 locations had all 9 candidates remaining. So we didn't solve very much, did we? And as time goes on, we do a lot of little steps here where we go and we turn these various dots into dots, but eventually we turn the 1 into a dot. And that undoes a great deal of our hard work. Essentially, we just have just the 2 now. And eventually we get rid of the 2, and we end up with just 9s everywhere. So that's rough. This is suboptimal for us. So let's let's tweak this a little bit and add in some of these rules and see if we can draw this down. And I want to do a few things actually. To minimize a lot of our headache here, I think I'm going to comment out if I can. There you go. Comment out this process by which we'd go and delete things because it's adding a lot of noise that we don't really expect to do anything good for us yet. At the end of the printout, and we're actually kind of keep our eyes on what's actually going on. But what I'd like to do actually is put a little print line in here. I guess just after the semi-join. And what this is going to do for us is let us observe observe each time a value becomes determined. So this set will have elements added to it, hopefully just added to it since we're just looking at this first round. Great. And what we would see are the arguments essentially to these uniquely determined locations. And everything that gets uniquely determined, possibly by being locked in or whatever, will eventually show up in here. The locked in values will go around the iteration once more and enter the determined set up here. But we're going to want to, okay, so this will just, we'll compile this while we're waiting. But the plan is going to be to add some more rules down here that correspond to these knights and kings moves, and also these orthogonally adjacent constraints. And I'll see if I can type all these out correctly. Morally, what we want to say is for each location like this one, we want to also rule out these locations here. So any determined location should also squoosh some things that we're gonna have to go in and relatively carefully write out, though, I mean, it's probably not going to be too terrible. We could do some other things, since we know these locations are going to be squished out also. We could be pretty clumsy and just squish out everything except these distant corners. We'll have to see what gets easily written. Hey, look. Okay, so over here on the right-hand side, we can see the two announcements about determination. So the one at location 5, 3 got determined. The 2 at 6, 7 also got determined. Is that right? 5, 3, yes. 6, 7 looks good. All right, and nothing else got determined because, yeah, there's nothing that goes on. So let's write some of these new rules. So let's do exclusions chess, I guess, because there are these two chess rules. There we go. Is determined dot flatmap. Flatmap because we are going to need to produce multiple excluded things, not just one. And flatmap is the method that lets us take one thing into multiple or zero things potentially. So what are we going to do here? For each of these locations, we're essentially going to want to consider potentially -2 up to +2, except for these extremes. So we could write a little iterator that does that. Right. So for our diff, let's say, in up to 3, because that's how there's probably some Rust inclusive language for these loops. I don't actually know what it is. It's probably got a 0 or something in it. But I'm not gonna make that up now. So do the same thing for rdiff and cdiff. We are going to want to what? If not rdiff. What's the right way to do this? I tried to use abs before and we got into some weird floating point crap. So maybe we won't do that. I mean, the easy, I feel so bad writing these sorts of things, but basically, if rdiff squared if this is not equal to 4, I can find the equals. All right, sorry. 4, or same thing for the cdiff. Oh my goodness. Ah, okay, good. Sorry, if you could see the keyboard I'm typing on, you would ask questions about why I was typing on this keyboard. It's a super sane question, but it's fun. Great. So if we're in a world where not both of these things are 2's, basically plus minus whatever 2's, then we're going to want to my word, we haven't written this out well, have we? We can't. Our closure here isn't going to be able to just yield because we're not in C++ or something like that, or C# rather. But so we're going to do this differently. We're going to make this into an iterator. So we've got a row diff and a cdiff, and we're going to want to restrict them down using the same rule. So don't anyone ever tell you that Rust is not a beautiful language. I mean, it's all my fault, I'm sure, but why don't let's try to make this a little tidier. Essentially, we're doing a join in here, so let's map this to. We might need to type a move, maybe. Cdiff to. Great. So what we've done is applied a flat map to produce all pairs of rdiff, cdiff things, which we should now filter down. Using both rdiff and cdiff. In the following way. And now apply them. To produce some rows, columns, and values. What format do we want here? We want a row and a column and then a value, it looks like. So let's do cdiff, and then we keep the value the same. And I'm gonna make let's see if this modification bites us. I'm a little hesitant to be using U8s everywhere because we're starting to use some negative numbers, and that's fine, but Rust is going to get a bit confused because it's not going to be really excited about that. So I'm curious if we go and we can change all of these things to be I8s instead. That may or may not bite us, but we'll see. So we've applied all these diffs. There's just one last thing we want to do, which might have worked anyhow. I don't actually know, but we want to remove anything that is not actually a legitimate board situation. So we want to make sure that row is bigger than 0, and row is I think that's how we start. Like we have rows. Yeah, they start at 1. Row is less than 10. And the same for column, that it should be great. And we return this as our iterator. And we call ourselves done. Now, we probably could have done some of these things like the mapping and the filtering after the flat map here, but we also might as well just do them in the iterator internally. So I'm just going to cargo check this. Okay, so there's a bunch of exciting issues. Val not equals. Okay, so somewhere else it looks like we've let things be U8s. Where have we done that? Oh God, just figuring out what Rust is up to is because these are bytes. All right, let's make sure they get converted as promptly as possible to count as IA. Now this is something that, oh geez, okay, this could be, well, we just have to rely on the fact. We'll see what happens. This is very bad behavior, but who knows what this actually is as an I8. Hopefully it'll let it wrap correctly. If this catches on fire, that's definitely my fault. There's some other things that are going on here. We are trying to compare references to things, and with references here, the row is a reference with concrete things, so we should put in little referencey symbols. See if I can. See what happens over here if we do that. Some closures that need to, okay, so the filter doesn't really care about the value. That's 100% true. This filtering wasn't based on the value, it was just based on valid board locations. We've got a few things that might outlive their, okay, yeah, we absolutely want to move. So this is where we start to reuse row, column, and value, and we want to be quite clear that we're happy moving these folks into these closures. Looks like that's the same thing it's complaining about over and over again. So let's great. So that compiles. Let's just run it to see if it's some exciting undefined behavior because of that I8 conversion. It shouldn't be because it's Rust, but it's totally possible that you can do too many funny things with floating point numbers and conversion. All right, so we're still seeing the same thing. That's great. We haven't actually used this this rule yet, so we could add this in. And try it again, and I don't actually expect that this will improve the world, but let's see. I think we need to be using the that one other rule too before we start making some forward progress. Hold on. Sorry. We successfully excluded ourself. Now that was definitely a mistake. So let's add another filter in here. Basically, we don't want 0, 0 as a thing to exclude, which hopefully you all totally believe. So we're just ruling out the possibility of both of them being 0, which definitely isn't a thing that we should be excluding. On principle, we could exclude all of the stuff, just like we did below, exclude all of the stuff, and then add in our determined results. Ugh. There's a great question about like what's the right way to clean up this code to make it a bit more clear what's going on. All right, this is a horrible tangle of a mess. Some comments would obviously help, right? Like actually explaining what this code does would definitely help. But we haven't gotten that far yet. All right, so we're still seeing only 2 determined locations, which is great because we haven't implemented that additional rule yet. So let's go do that. Let's write down that exclusions orthogonal. They use that word, which seems like a nice $20 word there. Where these are for any row, column, and value. Adding or subtracting 1 from the row or from the column shouldn't result in a value that is off by exactly 1 either. So let's do that. Also determined flat map, and I wonder if it makes some sense to think about like a different way than trying to write a horrible complicated iterator to solve this. Let's try it a different way at least. So let's try just we can put together a vector bad that is just an empty vector, sorry, up there, and we're going to add a few things to it. So we're going to add so bad dot push so we're going to add 8 things to this, I believe. 1, 2, 3, 4, 5, 6, 7, 8. So for example, row -1, we're going to add val -1 and val +1. Right. For row +1, we're going to do 2 things. We're going to add val -1 and val +1. And the same things over here for columns now. So for columns -1, we're going to add in a whole bunch of -1s, +1s, -1s, +1s. And now we're just going to return bad as the result. Now, we definitely don't look like a very smart computer scientist for writing all this stuff out, but I think it's a bit more likely that it's correct. Let's check it. Oh, I need a semicolon there. Yeah, it's not called vector, it's called vec. What kind of amateur hour Rust programmer am I on? Great. So this type checks, but we haven't used it yet. So let's before we use it, actually, should be a little careful. We kind of want to throw a filter on this as well, right, to make sure that we are not ruling out things that are off the board or potentially irrelevant values, right? To be honest, actually, it's probably not all that bad because what we're going to do is go through and threshold things based on keep the things that are 1, ditch everything else. So we feel a little silly maybe because we've got some negative locations that are off the board, but they won't have any positive support in the first place, so they'll just vanish here. So I think this actually we don't even need to do that bit of logic. It's a theory. One thing that's delightful about watching these Sudoku videos, by the way, is that the guy doing them isn't wrong. He doesn't make screw-ups like I probably am making all the time, which is a very reassuring sort of thing to watch. Makes you feel that all is right in the world. All right, so we've now got some more exciting stuff going on here. You can notice that we have some determined locations up here. These are the ones we started with. the 1 and the 2 here and here. But we've got some other locations now too. Apparently, and I can walk you through some of this reasoning, apparently 4, 6 needs to be a 1. So 4, 6 is this location, and the claim is that it needs to be a 1. And let's talk through the reasoning for that. I can explain. So in particular, this 1 blocks out a lot of stuff, right? So it blocks out all of this content, all of this content, all of this content, all of this content. These are just by normal Sudoku rules. But by the chess rules, it also blocks out those two, king's moves and knight's moves. This location is immediately adjacent to a 2. So it also cannot be a 1, and this, for what it's worth, also can't be a 1. Leaving this as the only possible location that we can have a 1, which is super exciting. Yeah. We determine a few other locations too, which are interesting. I'm curious, hopefully these are not wrong. We determine that 5, 1 has to be a 2. 5, 1, so this location has to be a 2. It's a good question why that necessarily follows. Let's see if we can figure it out. And 6, 9 needs to be a 1. This is a bit more obvious, I think, because this 1 here, once we've inserted it, blocks out by king's move. King's move down here and by knight's move here, and normal Sudoku these locations. This 1 blocks out this nonsense here, and this cell is forbidden because it's immediately adjacent to the 2. So that means that definitely can't be anywhere except down here, so we can set this to be a 1 also. I'm curious to try to figure out, and we can do the reasoning about the 2s. The thing that surprises me a little bit is it happens to be in the exact same round. So I might have imagined this to be in a subsequent round of derivation, but possibly... Well, what's going on is in the 0th round, remember this printout is up at the very top here. So we're initially announcing those folks that are determined right now. We then apply our exclusions, which cause some people to become determined. The reasoning that I applied only really caused this one to be determined. This location is still totally open until we learn that this is determined, because these places could be ruled out. However, having made various things determined, having applied those exclusions, we then apply these other bits of inferencing that say if you're the only place that could possibly that's still valid, you need to be a uniquely identified representative, which is actually probably what's causing this 1 to light up, because these locations were already ruled out ahead of time, like when we started the loop. The Sudoku constraint from the 1 and the adjacency constraint from the 2 were ruled out from the get-go. The determination, once we've picked this location and squooshed a whole bunch of other things, this becomes the only valid member of the cell, I'm guessing. Like it's not the only member of a row. I'm not exactly following. So I think it's pretty interesting, and I want to track this down to figure out how this became determined so quickly. I was sort of expecting one fact to show up each round. This is the first time I'm looking at this, by the way. Have these show up each round, one by one. Let's see if we can similarly figure out why it decided that this needs to be a 2. And in particular, let's hope that that's actually true. And there's not some miserable off by 1 error or something like that. For example, I would have thought that that the next 2 would have to show up in this cell over here. And I'm a little worried that something weird is causing these options to be ruled out. These seem like, these locations can't be a 2. These locations can't be a 2. And something prevents these locations up here from being a 2 also. And I don't know what those are. And I'm hoping it's not something dumb like wrapping around some of these rows and columns or some miserable logical error. But let's check it out. I'm going to delete this just for the moment, because we can move forward and figure out where the other 2 is. 4, 4 needs to be a 2, apparently. That's this location. That one totally makes sense to me. It makes sense that we would be able to conclude that. This location is ruled out from being a 2. This is also. These locations are ruled out from being a 2. And, this location is also ruled out from being a 2. So it makes sense that this is the only possible 2 location. What we might have concluded, interesting. Great. Okay, so this was the reasoning. Here, this location also can't be a 2, and this one can't be a 2. So just from this, without thinking very hard about this location up here, we can already determine this is the only valid place for a 2 to be still. And we can leap immediately to concluding that the 2 has to be there. So that's neat. The differential Dataflow program realized something that I didn't realize. Pretty sweet. Nice job. And in the next iteration, so these 3 things I think are all actually justified as legit conclusions, including one that I wouldn't have made. So good thing that differential Dataflow is here to help us out. We then leap to a few more conclusions. That 3, 1 has to be a 1. 3, 1 is this location. Has to be a 1. Great question why that is. There's a different field of big data processing things where we try to explain the results of so when I show you a result in the output, explain why, like what rule is fired, or like what facts in the input were actually used to determine this. And it's a great question. I'm not actually sure what causes this to be a 1, but we can try to apply some of these bits of inferencing and figure it out. It may also be a consequence of this other thing that gets determined, that 4, 4 has to be a 2. So this location has to be a 2. We've decided, and we saw that already by noting that all of these locations are ruled out. So this has to be a 2. Great. This 2 prevents this location, and in fact, all of these locations from being a 2. This 1 prevents these locations from being, hold on. I'm screwing up this explanation, sorry. With this 2 in place, we might ask, and let's imagine we don't actually know about this one yet. With this 2 in place, we might ask, where can there be a 1 in this row? And this 1 prevents these 3. This one here, oh goodness, prevents these 3. This one here prevents all of these folks. And then this column 1 prevents this folks. So this is definitely a 1, or it has to be a 1 for exactly that reason. This continues now. 7, 3, and 7, 5 get determined to be 2s and 1s. So 7 down here, 3 and 5 become apparently a 2 and a 1. Is that believable? Possibly. This 2, the main thing to notice is that things like this 2 really blots out a whole lot of area. It blots out all of these locations from being 2s. This 2 in this column says that this entire column can't be 2s, and this 2 over here again covers a whole lot of ground. I won't draw all these. Yeah, anyhow. So it says all these things can't be, and at this point you can see that the only location for a 2 in this entire row 7, is this location. And I'm going to guess that some similar reasoning, who knows, is going to require that the 1 be here. Let's see if we can reconstruct that. So the 1 isn't allowed to be here because it's next to a 2, and this 1 also blocks it out. Can't be anywhere here. What are some other good reasons that we can't have the 1 has to be here? Is it going to be because of this row? The 1 prevents it from being there. Oh, sorry, also the 2 prevents it from being there. 2 prevents it from being there. This 1 prevents it from being any of these locations. And this 1, good, right, this column prevents it from being here. So now this is the only place that 1 can exist. Good. But by the way, if you watch the nice Sudoku video, the man is actually producing all these derivations using his own brain, whereas I'm using my brain to try to figure out what the heck differential Dataflow did, which is a different brain teaser. Actually, it's definitely interesting to try to figure out what in the world has gone on. But they check out so far. All right, 8, 2, 9 are 1 and 2 respectively. So 8, 2, and 9 got set. And this is somewhat believable. I'm not entirely sure in which order we figured these things out. That would have been helpful. So a nice thing about breaking up these rules a bit more, making them more sort of in parallel rather than in sequence, is that the sequencing of the derivations would be a lot more clear. We would see in different rounds things that only followed from facts in a strictly prior round, which would be a lot clearer, for sure. So, beg pardon. How might we go about determining either this fact or this fact? This 2 blots out a fairly large region there. This 2 kills everything else there. So that 2 has to live in that location. And with that having been locked down, why is there a 1 here? Well, this 1 blocks out a fairly massive region. Sorry, not that one. Blocks out a fairly massive region. This location is ruled out by the 2. So this is off by 1 from 2. And this location is blocked out by the column. Which leaves us with this as the only possible location for the 1. And we can continue. 3, 8 gets fixed next as a 2. 3, 8 fixed as a 2. 2, 2, and 2, 4 are 2 and 1, I believe, respectively. 2 and 1. And the derivation stops at this point. 14 locations were uniquely determined. Good for us. The next closest we got to having unique derivation was a location that had 6 different possible values. So we're going to continue. We're definitely going to need to think a bit harder. And that is, I think that's going to be the subject of the next video. This is a great time to stop. And I'm going to leave us there to think a little bit about. I mean, you can watch the cracking Cryptic video and see the bit of reasoning that happened to figure out where the 3s must be. But we'll get there, and hopefully we'll find that we've written a totally tractable, reasonable differential data flow program to get there. But for the moment, we're gonna stop.